Hello students, I welcome back you to this unit number 3 where we are going to start the working principles of vapor absorption systems. So far we have seen vapor compression system. Now we are going to start vapor absorption systems where we are going to see different topics. So these are the topics from unit number 3. The title of unit 3 is Other Refrigeration Systems. So first topic is working principles of vapor absorption system, and same topic, it requires one more session, and after this vapor absorption system second session, let us discuss about Electrolux, the first refrigerator, so that works based on the vapor absorption system. So I am going to take 3 sessions on vapor absorption systems where I am going to include the Electrolux refrigerator, and then the cooling systems we are going to see. Then steam jet refrigeration, it is also called as ejector refrigeration system, thermoelectric refrigeration, air refrigeration, magnetic refrigeration system, vortex tube refrigeration system. So these are the topics, and the last one in this unit is pulse tube refrigeration system. So these are the topics in our unit number 3 where we are going to discuss all these topics elaborately. And let us start the first one, working principles of vapor absorption system. And first we cover the theory. Later we will see few numerical problems, and then we will move on to the Electrolux type vapor absorption system. So these are the content from unit number 3. So we are starting unit 3 today, and we are going to complete this in coming 9 more sessions. So in 9 more sessions we are going to discuss more about other refrigeration systems other than vapor compression refrigeration system, where we have covered that in our earlier unit. So let us see the introduction to the vapor absorption refrigeration system. So if you see the definition and historical background of this is very simple, and the vapor absorption refrigeration system is one of the oldest methods. So this is very old method for producing refrigeration effects. So already we have seen the vapor compression refrigeration system that is more widely used than vapor absorption system. The principle of vapor absorption was first discovered by Michael Faraday in 1824. In this year, almost uh, 200 years before, while performing experiments to liquefy certain gases. So gases, he tried to liquefy the gases. So he wanted to produce liquids out of gases. The first vapor refrigeration system, that is machine, was developed by French scientist, that is Ferdinand Care. So in the year 1860 itself. So Ferdinand Care has produced the first refrigeration system based on vapor absorption refrigeration system. So this system is used in both domestic and large industrial refrigeration plants. So working principle of vapor absorption refrigeration system. This system commonly uses ammonia as refrigerant, which absorbs heat via a series of processes. Unlike the vapor compression system, which use mechanical energy to compress the refrigerant, vapor absorption systems use heat energy to drive the cycle. So here it is little contrary to the vapor compression system, where here it uses mechanical energy to compress the refrigerant. Vapor absorption systems use heat energy to drive the cycle. So instead of compressing the refrigerant, we are using the heat energy to drive the cycle. So that is the basic principle of the absorption system. So absorption versus compression, these are the two widely used systems, but the compression system is more popular. The vapor absorption system does not require mechanical compressors as in vapor compression systems. So there are no compressors required. Instead, it relies on an absorber or a pump and a generator and a pressure reducing valve to cycle the refrigerant. So here, instead of compressor, we are using an absorber, a pump, a generator, a pressure reducing valve. So these are the four main components. So that is absorber, pump, generator and pressure reducing valve. So these are the major components we are going to see in this particular topic. So use of heat energy. So this system requires an external heat source for operation, replacing the mechanical energy input that is seen in vapor compression systems. A simple vapor absorption system, the components of the system are absorber. It absorbs ammonia vapor, so low pressure ammonia vapor, and pump, so increases the pressure of the ammonia solution, and generator heats the solution to release ammonia vapor, and pressure reducing valve reduces the pressure of ammonia vapor to allow its further expansion. So pressure reducing valve is a very important component because it reduces the pressure of the ammonia vapor to allow its further expansion. So further expansion it arrests. So condenser also required here. It condenses the ammonia vapor back to liquid state. A receiver, here a receiver is required. It stores ammonia refrigerant in liquid form before returning it to the evaporator. Evaporator, the point where the ammonia evaporates, absorbing heat to provide refrigerant. So these are the main components of absorption system. The first one is absorber, next one pump, generator, pressure reducing valve, a condenser like in vapor compression system, and a receiver and a evaporator. So these are the major components of the vapor absorption system. So working principle, the system is driven by low pressure ammonia vapor that leaves the evaporator and then enters the absorber. In the absorber, the ammonia vapor is absorbed into a solution, usually water, so forming a weak solution. The weak solution is pumped to the generator where it is heated by an external heat source. So during this heating process, ammonia vapor is driven off from the solution and enters the condenser. So the condenser then condenses the vapor into liquid ammonia, which flows through the receiver and is then expanded back into the evaporator to absorb heat, completing the cycle. So here in the condenser, it absorbs the heat and where it is expanded, and it also back to the first stage of the cycle. So the schematic of vapor absorption system. So this is the complete picture. So now this is a cyclic process. So this is a cyclic process. It starts from the absorber. So heat is rejected here, that is QA. So this is cooling water is circulated in the absorber, and the ammonia vapor enters, that is from evaporator, and enters the absorber, and it becomes the strong solution. So it becomes a strong solution. So where you have connected the pipe pump, this pump pumps the flow, that is the refrigerant, ammonia vapor refrigerant, to the generator. So generator here, heat supplied here, so heat is supplied in this steam or heating coil. So here a steam or heating coil is provided. So weak solution is fed back to absorber, and here a pressure reducing valve is provided in this the returning line, but the strong solution, that is high pressure ammonia vapor, is supplied from generator to the condenser. So here cooling water is circulated and the heat is rejected here also. So this is the main cooling chamber, and where the heat is rejected majorly, and from condenser the liquid ammonia is sent back to receiver. Receiver receives the liquid ammonia, and this receiver expands. This receiver supplies the liquid ammonia to the expansion valve, and this expansion valve supplies the liquid ammonia to the evaporator. So heat is absorbed here in evaporator. So this is the condenser where mainly the heat is rejected, and this is known as the refrigeration space. And this is the complete picture of vapor absorption system. So we see the components in detail. Now one by one we will discuss. The absorber. In this component, low pressure ammonia vapor leaving the evaporator is absorbed into strong ammonia solution. The solution absorbs large quantities of ammonia due to its physical property of being a solvent for ammonia vapor. The water used here acts as an absorbent and taking in the ammonia vapor at a low pressure. So absorber the ammonia vapor is will be at low pressure only. So next component is pump. So the pump then increases the pressure of ammonia solution. So there it becomes strong ammonia solution. Strong is nothing but here the high pressure. It acquires high pressure due to pumping process to a higher level, typically to 10 bar. So 10 bar pressure will be there to the ammonia solution here after the pump. The increased pressure helps move the solution towards the generator. So next is generator. So generator, here the generator is where the ammonia solution undergoes a heating process, often by using an external heat source such as steam or gas. Even a electric coil can be used here. In this process, ammonia vapor is driven off from the hot ammonia solution and enters the condenser, leaving behind the strong ammonia solution that is recirculated. So next component in the cycle is condenser and receiver. So condenser, the ammonia vapor is cooled and condensed back into a liquid in the condenser, where it is stored in the receiver. The liquid ammonia is then passed through a pressure reducing valve and expanded to its original evaporating pressure before being returned to the evaporator. So the figure that I have shown in the earlier slide, so that is the major diagram. All of you please practice that diagram. So additional considerations, the absorption and heat exchange. So the system works on the principle of using ammonia vapor at a lower temperature and pressure to absorb heat. The heat supplied to the generator causes the ammonia to evaporate from the solution, releasing the vapor into the condenser. Water as absorbent. And a key point about the system is the use of water as the absorbent, which is essential for absorbing ammonia vapor and ensuring the efficient operation. So the weak ammonia, so that is weak ammonia is nothing but at low pressure. Solution formed in the absorber is pumped to the generator, where it is heated, releasing ammonia vapor and leaving behind a stronger solution. So here from this we have to remember these points to remember. The vapor absorption refrigeration system is an effective method for refrigeration, particularly where waste heat or low cost energy sources are available. Unlike the vapor compression refrigeration system, which uses mechanical energy, the vapor absorption system uses heat energy, making it more suitable for environments where electrical energy is costly or unavailable. The system is used across different scales, from small domestic refrigerators to large industrial refrigeration units. So next we see the schematic of practical absorption system. So this is the schematic where we have absorber. So here cooling water is circulated, and we have a pump, and through heat exchanger is provided. So in practical absorption system, a heat exchanger is provided here. So another heat exchanger is provided along with the evaporator here, and this heat exchanger, through heat exchanger, the pumped refrigerant is supplied to the cooling, that is the rectifier is provided here to rectifier through the generator. So generator here, it produces the heat, and now this heat is clubbed with this refrigerant and send it to the cooling water, that is the rectifier, or it is also known as dehydrator. So from dehydrator is it is sent to the condenser. So this is the our practical refrigeration space, and cooling water is circulated here. So from this we have receiver, and then through heat exchanger, through heat exchanger and expansion valve, the refrigerant reaches the evaporator. Again through heat exchanger, it sent back to the absorber. So this is a cyclic process again, and each component we will see in detail. The simple vapor absorption system discussed in the previous sections is not very economical for large scale applications. To enhance the system's efficiency, several modifications are introduced as depicted in this figure. These improvements involve the use of an analyzer, a rectifier, and the heat exchangers to enhance the performance of the system. So the first component is analyzer. The analyzer is used to in the generator where ammonia is vaporized and water is also evaporated. This process ensures that unwanted water particles do not enter the condenser along with the ammonia vapor. So that is why we have analyzer. So this actually eliminates the unwanted water particles, so that enter the condenser. So that is eliminated using an analyzer. The analyzer helps in the separating the ammonia vapor and ensuring the ammonia leaves the generator without mixing with unwanted vapor, water vapor. The water vapor is removed from the ammonia vapor by passing it through a special analyzer, which can either be a built-in component of the generator or a separate unit. So we can provide an external one also. In the analyzer, ammonia vapor 98% is separated from water vapor, which is condensed and returned to the generator. So a considerable amount of water vapor may leave the generator, but the analyzer effectively reduces this, improving system efficiency. So the main function here, it removes the water particles or water vapor from the ammonia. So that is the major advantage, and effectively increases the efficiency of the absorption system. Next we have rectifier. So the rectifier is used to handle the remaining water vapor not completely separated by the analyzer. So there will be residues of water particles. So that should be removed. So here a rectifier is used for that purpose. It operates by cooling the ammonia vapor and removing residual water vapor. The ammonia vapor passes through the rectifier. It is a closed type cooler where it is cooled and condensed. Only dry ammonia vapor with negligible water content is passed on to the condenser. This ensures that the ammonia in the system is of high purity, improving overall system performance. So here it is like a purifier. It is used like a purifier, the rectifier. Then we have heat exchangers. We have two heat exchangers as shown in that figure. Heat exchangers are used between the pump and the generator to cool the weak solution returning from the generator to the absorber. This removes the heat from the solution, reducing the temperature of the strong solution. And cooling is also applied between the condenser and evaporator. It is a subcooling process. It is called a subcooling process where the liquid refrigerant is cooled by the ammonia vapor leaving the evaporator. So impact on efficiency, the heat exchangers reduces the heat supplied to the generator and the amount of cooling required for the absorber, improving the overall economy of the system. So heat exchangers are effectively used in this absorption system, and also it increases the efficiency as well as the economical economy also it provides. So that figure already we have seen. The complete layout we have seen there. Practical vapor absorption system including analyzer, rectifier and heat exchangers. The system includes the following components. The first one is pump. Pump sends the strong ammonia solution to the generator, and absorbs ammonia vapor into the solution. Condenser condenses ammonia vapor into liquid form. A receiver holds the condensed ammonia refrigerant. Evaporator absorbs the heat from the surrounding environment. And expansion valve, it reduces the pressure of the refrigerant before entering the evaporator. And the integration of these components ensures high efficiency and reducing the overall operating costs. So that is the advantage of having these components in the vapor absorption system. So the major components are pump, absorber, condenser, receiver, evaporator, expansion valve. So coming to the performance measure, so that is nothing but coefficient of performance. The COP of the vapor absorption system is defined by the following equation. So heat absorbed in the evaporator divided by work done by pump plus heat supplied in the generator. So this is the COP of COP can be calculated for the absorption system. This formula helps assess the energy efficiency of the system, indicating how much refrigeration effect is achieved per unit of energy supplied. So thermodynamic requirements of refrigerant absorbent mixture. The performance of the vapor absorption system is heavily dependent on the characteristics of the refrigerant absorbent mixture. The two primary thermodynamic requirements must be satisfied. They are solubility requirement. The refrigerant must have a high solubility in the absorbent, allowing the absorption of the refrigerant vapor into the solution. Next, boiling points requirements. So there should be a significant difference in the boiling points of the refrigerant and absorbent to facilitate the separation of ammonia vapor from the absorbent. So additionally, we need this. The mixer should exhibit the following properties. Low viscosity for ease of pumping. So low viscosity is preferred here, and a low freezing point to avoid crystallization during operation. So good chemical and thermal stability to avoid degradation of the solution, and no significant irreversible chemical reactions are required. So there should not be any irreversible chemical reactions. So properties of ideal refrigerant absorbent combination. The ideal combination of refrigerant and absorbent should have the following qualities. High affinity for absorbent at low temperature. The refrigerant should have a high affinity for absorbent at low temperature and lower affinity at higher temperatures. So this is the major requirement. A negative deviation from Raoult's law. So the combination should exhibit a high degree of negative deviation from Raoult's law, which is essential for efficient absorption. So non-corrosive mixture, the mixture should be chemically stable and non-corrosive, preventing damage to system components. So this is another essential property. So low freezing point. The mixer should have a low freezing point to prevent solidification at low temperatures. So small heat load. The solution should have a small heat capacity to minimize the thermal load on the system. Commonly used combinations are ammonia water combination, lithium bromide water combination for large industrial applications. So this is another popular absorption system, bromide water combination. So we have another comparison here. The comparison of refrigerant liquid absorbent and refrigerant solid absorbent combinations, and this is small comparison, and it is also one of the important questions in exam point of view. The liquid absorbent system, it is obviously ammonia and water. The liquid absorbent system is most commonly used in the vapor absorption cycle as it provides a good balance of efficiency and performance. Solid absorption system were more robust. It is more robust, but less sensitive to external environmental conditions. However, their performance is less efficient compared to liquid systems in terms of heat transfer and absorption capacity. The solid absorbent systems are ideal for applications that require intermittent operation or where environmental conditions are highly variable. So the example is solar energy systems. So the COP comparison, coefficient of performance. The coefficient of performance of solid absorption systems is generally lower than for liquid absorbent systems due to the inherent heat requirements in the solid system. So this is another important point. So the coefficient of performance for solid absorption system is generally lower than the liquid absorbent system due to the inherent heat requirements in the solid system. So solid system provides lesser COP because of the inherent heat that is there in the solid. We see the advantages of vapor absorption systems over vapor compression systems. We already we have discussed vapor compression system in an earlier unit. So no moving parts in absorption system. The vapor absorption system has no moving parts like the compressor in vapor compression systems. This results in reduced wear, tear and noise. Heat energy use. The absorption system uses heat to drive the refrigeration cycle, unlike compression systems which rely on mechanical energy. So efficiency with low or high pressure. The absorption systems can be designed to operate at lower or higher pressures depending on the application, making them more flexible. Use of waste heat. This system can utilize low-grade heat from waste sources like solar or furnace steam, making it highly efficient for sustainable applications. So then the less dependence on electrical power. It operates well even when electrical power is unavailable or unreliable, unlike vapor compression systems, so which require electricity to run the compressor. So in vapor compression system, we require electricity to run the compressor, whereas here we have less dependency on electricity. So compactness and flexibility. So compactness and flexibility, the vapor absorption systems are more compact and flexible, capable of being designed for various sizes, especially for solar power or small scale refrigeration systems. So that is another advantage with this vapor absorption systems over compression systems. So coefficient of performance of an ideal vapor absorption refrigeration system. The coefficient of performance is crucial parameter in evaluating the efficiency of refrigeration systems. As we know that already we have discussed enough on coefficient of performance in our earlier unit also. In an ideal vapor absorption system, refrigeration system, the COP is determined based on the heat energy supplied and absorbed during refrigeration cycle. The following points outline the key aspects and calculations related to COP of an ideal system. So basic assumptions, heat transfer in the system. The following heat exchanges occur in the ideal system. So that is heat Qg is given to the refrigerant in the generator. So Qc is discharged, heat Qc is discharged to the atmosphere or cooling water from the condenser and absorber. So C is QE. QE is the heat absorbed by the refrigerant in the evaporator. and QT is the QP is the added to refrigerant due to pump work. So first law of thermodynamics is considered here. According to the first law of thermodynamics, the total energy balance in the system can be written as QC equal to QG plus QE. So QG is the refrigerant heat given to the refrigerant in the generator, and Q is the heat added to the refrigerant by heat absorbed by the refrigerant in the evaporator. So the small derivation here. So Tg is temperature at which heat Qg is given to the generator. So Tc is temperature at which heat Qc is discharged to the condenser or cooling water, and Te is the temperature at which heat Qe is absorbed in the evaporator. So from the entropy balance equation, since the system is considered ideal, so Qc by Tg plus Qe by Te equal to Qg by Tc. So this is the energy entropy balance equation, and simplifying this equation, that is Qc by Tg equal to Qe by Te. So this from this relationship we can derive the expression for the Qg. So Qg can be calculated Tc by Te into Qe. So the maximum coefficient of performance of the system is given by the ratio of heat absorbed by the refrigerant in the evaporator to the heat supplied in the generator. So COP max equal to QE by QG. So equal to QE by QE plus QP. So here the expression Tc by Te represent the COP for a Carnot refrigerator, where Tc is the temperature of the cooling medium and Te is the temperature of the evaporator. So the expression Tg minus Te divided by Tg minus Tc is the efficiency of a Carnot engine, where Tg is the temperature of the heat source generator and Tc is the temperature of the condenser. And you can remember these key insights from these formulas, and here this is the simple diagram where you can remember all the T's and Q's, and this is the TE temperature of refrigeration, that is the evaporator temperature, and it is given to refrigerator here, and Tc equal to Ta, that is the temperature of condenser and absorber. So both are equal, and from here QA is supplied from engine to refrigerator, and engine to from engine we are having the QG from TG, that is the generator temperature of heat source, that is generator, and QG is taken by the engine, and QA is given by the engine. So QA is the absorber heat energy, heat source. So this is simple diagram, you can remember very easily, students. The ideal vapor absorption refrigeration system can be considered a combination of a Carnot engine and a Carnot refrigerator, as shown in this figure, to produce the desired refrigeration effect. The maximum COP of the system occurs when the heat is transferred between the temperatures of the condenser and evaporator, and is represented as the COP max equal to COP Carnot into efficiency of Carnot engine. So the system is considered as Carnot engine here. Efficiency of the Carnot refrigerator. So here you can see it is crucial to note that the ideal system performance is limited by the Carnot engine efficiency, which dictates the relationship between the temperatures at different points in the cycle, that is condenser, evaporator, and etc. So these points are considered, and the efficiency of the Carnot refrigerator is defined like this. So here the representation of the vapor absorption refrigeration system consists of generator, absorber, condenser, evaporator. So from the earlier diagram, so we can correlate the same diagram, or we can match the same diagram with the refrigeration system. So here generator, the where heat Qg is supplied, absorber where ammonia vapor is absorbed, condenser where heat Qg is discharged to the cooling water, or atmosphere. Evaporator, where QE, heat QE is absorbed from the surroundings to produce the cooling effect. So implications of coefficient of performance. So here the maximum COP. So formula highlights that the efficiency of the ideal vapor absorption system is significantly affected by the temperature difference between the evaporator, condenser and the generator. A high temperature difference between the evaporator and condenser results in a lower COP, indicating that systems must be designed to minimize these temperature differences for optimal performance. And waste heat utilization. Here in real systems, the waste heat from industrial processes or solar sources is often used to heat the generator, improving the overall energy efficiency and increasing the COP. So waste heat utilization, that is the due to from industrial processes or solar sources, so that can be used here in the generator. So coming to the conclusion of the theory of this particular vapor absorption system, these points you should remember, students. The COP of vapor absorption refrigeration system is the fundamental in determining the system's efficiency. The ideal systems operate based on principles similar to those of Carnot engines and refrigerators. The maximum COP is achieved when the heat energy is transferred effectively between the various temperature limits of the system. By optimizing temperature differences and integrating waste heat recovery, the performance of the system can be enhanced. So this is the very important point. So by optimizing temperature differences and integrating waste heat recovery, the performance of the system can be enhanced. So these are the points to remember from this topic. And students, we stop here. In next session, we will see a few numerical problems on this topic, and then we will move on to next Electrolux refrigerator. So these are the references. So please refer these references, and I prefer Kurmi gives you complete information for on this topic. Please refer either Kurmi or our regular textbooks, Rajput or Aurora, CP Aurora. So you can refer any of this, and we stop here, and we will move to next topic in next session. Thank you, students.